Hello and welcome to Quantum Algorithms and Cryptography. I am Shweta Agarwal from IIT Madras. So let me tell you a little bit about what this course is all about. Let's first of all begin just with looking at cryptography. So what is cryptography? As many of you know, it's the science, the art really of keeping secrets, and it comes with strong mathematical guarantees for security. And what do these guarantees look like? Well, typically the kind of thing that you're able to say is that breaking a crypto system is at least as hard as solving some difficult mathematical problem. And being computer scientists, we model this as a reduction, right? So we say that assuming there is some adversary shown here as attacker A that can break our crypto system, there exists some sort of wrapper, what we call a reduction around this adversary that takes as input an instance of some hard problem X, massages it into an instance of the crypto system that the attacker is supposed to break, and then translates the break given by the attacker into a solution for the original problem. So now if we choose our hard problem suitably well, then we don't expect this attacker A to exist, right? Because the existence of attacker A implies a solution to this problem which we don't expect to happen. Now, one of the things that I've brushed under the rug is what do I mean by difficult? So, in particular, difficult for whom? Right? And this is the quintessential cryptographic adversary. The who is the cryptographic adversary who's normally modeled as a classical computer. And the typical guarantee that we get is that unless the adversary can solve this hard problem in some clever way, just a brute force approach to solving the problem, or whatever is the state of the art way of solving the problem, takes more than, let us say, the age of the universe. So we can set the size of the problem to be big enough that the time that it's expected to take to solve this problem is an unphysical number, like something very, very big. And moreover, this guarantee is robust to the type of computer you use. So it really doesn't matter whether you have a mobile or a supercomputer. The formalism, gracefully handles these differences. But it turns out that things change quite significantly if we change not the quantity of a given resource but the quality of it. So instead of modeling the adversary as a classical computer, if we now model the adversary as a quantum computer, then it turns out that things start looking very different. So what are quantum computers? These are a fundamentally new paradigm of computing that essentially use the laws of quantum physics rather than classical physics. And in some cases, they are shown to have exponential speed ups over existing algorithms, existing classical algorithms. Now, most modern day cryptography relies on the hardness of certain number theoretic problems like factoring and discrete log, and these are actually broken if quantum computers are realized. So before we move on, it's worth asking, is this threat real? I mean, is this just something that we're studying out of scientific curiosity, or is this really a problem? And the short answer is that this is really a problem. And there have been, a long sequence of articles that we have seen, here's one from a few years ago, where companies, government labs and so on claim that they have built a quantum computer that can outperform a classical computer on a given task. So there have been a lot of strides in the development of quantum computers. And even let us say that it takes 5 years to get a powerful quantum computer, or it takes 50. The point is that scientifically speaking, it is something that we need to prepare for. And if cryptography is broken using a quantum computer, then this is really a state of affairs that needs to be addressed. And this threat, this urgent need of upgrading cryptography to be post-quantum is well acknowledged worldwide. So, for example, the National Institutes of Science and Technology in the United States has long since initiated a process to solicit, evaluate and standardize quantum resistant cryptography, and there has been a significant global research effort on this front. So now let's come back to our course. Okay, so what is our course going to be about? Well, we'll start with discussing the foundations of quantum computation. So, the mathematical model for quantum mechanics, quantum gates and quantum computing, some quantum algorithms that outperform classical algorithms. So, we will see several of them. Perhaps the most prominent ones are Grover's algorithm for unstructured search and Shor's algorithm. These are two algorithms that have a direct impact on cryptography. Having seen how these algorithms can break existing number theoretic cryptography, we will try to see what can be done to redress this situation. Okay, so how can we build quantum resistant cryptography? So essentially what is meant by quantum resistant cryptography or post quantum cryptography is that this is cryptography based on the hardness of problems that are also believed to be hard for quantum computers. Okay, so we will take some hard problem and now this, when I say hard, it is not just hard for our traditional classical adversary, it is also hard for, at least believed to be hard for, a quantum adversary, and we will try to build our cryptography based on that. Now there is a lot of things that one needs to be careful about. So, just choosing the hard problem to be quantum resistant turns out not to be enough, but let us see when we get there how much we can discuss it. Okay? So, at the very least we will do a few basic cryptographic protocols like key exchange, public key encryption, and one cutting edge cryptographic primitive known as homomorphic encryption, which was a big breakthrough in recent times. We'll study that. And then having seen how to prepare against quantum computers breaking cryptography, we'll then shift our attention to see whether quantum computers can also help cryptography. So, can we do better? Right, and there's also been enormous success along this front. So, I think the most famous example is the key exchange protocol, right, from BB84, which gives us a perfectly secure key. Okay, so we'll see how to use quantum computation to do key exchange. We'll see how to further leverage those capabilities to get a one-time pad public key encryption, and then lastly we will see quantum fully homomorphic encryption. So, sort of to match the classical fully homomorphic encryption, this will be about evaluating quantum circuits homomorphically on encrypted data. So, if some of these terms do not make sense for you right now, do not worry about it. We will define everything as we get to it in the course. This is just to give you a flavor of what to expect. Okay. So, now let me just briefly touch upon some of these aspects that I mentioned. So, first let us talk very briefly about the foundations of quantum computation. As you are aware, the famous Church-Turing thesis says that any reasonable model of computation can be simulated by a Turing machine. And there is an extended or a strong version of this thesis which says that any reasonable model of computation can in fact be simulated efficiently using a Turing machine. Okay? So, that means up to polynomial time reductions. Now, a natural question which arises in the context of quantum computation is, what about quantum mechanical processes? Can these also be simulated efficiently by Turing machines? Right? And it turns out that there are examples where this is not known. Okay, so there are efficient quantum algorithms that perform tasks that are not that do not have known efficient classical algorithms. So, as I already mentioned, the most promising or the most famous example of these quantum algorithms are those that break modern day cryptography, that break factoring, discrete log and other hard problems on which cryptography is based. Okay, so this may offer a potential counter example to the extended Church-Turing thesis. Now, you may have noticed that these seem like very basic questions, and do we really not have answers to these? So yes, indeed, it turns out that despite these questions sort of seeming so fundamental, we in fact understand very little about it at the moment, and we have exciting times to look forward to, where hopefully we can see some of these questions being answered, even if only partially. So we'll study a mathematical model for representing quantum computation. I already said this, right? Quantum circuits, quantum gates, quantum algorithms, speed-ups over classical algorithms, and culminating with Shor's algorithm, which breaks these cryptographic assumptions. Then we'll move on to post-quantum cryptography. Yeah, so I already said that this is where we base cryptography on the hardness of mathematical problems for which quantum computers have no advantage. Here we'll particularly focus on problems in high dimensional lattices. Okay, so a lattice is a mathematical structure that has given rise to some really beautiful cryptography, very interesting and elegant in its own right. I mean, even forgetting the post-quantum advantage. And we'll have a chance to dig deeper into some of these problems. We'll discuss why these problems are believed to be quantum hard, and then how to do interesting cryptography with that. Okay, so this is a very sort of toy example of a lattice and a hard problem on a lattice. A lattice is, you can think of it as a periodic arrangement of points. A little more formally, it's a discrete subgroup in Rn, and it can be, it is represented by some basis. Okay, so I have two vectors, let's say v1 and v2, and integer linear combination of them will generate the whole lattice. These bases are not unique. So given a basis, finding the shortest non-zero vector in the lattice, this is one of the problems that we believe is hard for a quantum computer. Okay, so we'll see how to build cryptography from the hardness of this problem. So the most beautiful example of what can, well, this is a subjective statement of course, but I think that the most beautiful example of the power offered by lattices is that of fully homomorphic encryption. And this is a very famous application. If you haven't seen it, let me just tell you very briefly what it lets us do. So essentially it lets you compute blindfolded. Okay, so what that means is that generally if I have some information, right, and I want to compute some mathematical function on it, and I want the output of this computation to be encrypted, then common sense tells me that I should do the computation before I encrypt the data, because once I encrypt the data, the security of encryption will say that this ciphertext should look like junk essentially, and I should not be able to do anything useful with that junk, right? So common sense will tell me I should do the computation. Let's say my input is x, let's say my function is f, I should compute f of x and then I should encrypt it. This is the obvious way of doing this. Well, fully homomorphic encryption tells you at a very high level that actually encryption and computation commute. So that means that I can encrypt the data first, compute on it while it is still encrypted, right? So I encrypt x, compute f on encryption of x, and end up with an encryption of f of x. So it's really beautiful stuff. We'll see how it's done. Here's an example of how it is used. Okay, you have some private data. Let's say that I am a client, I don't have computational power to compute f, f is some large circuit, I just have a mobile phone, I can't compute it. But I have an account with Amazon or something, and I would like them to compute it for me, but I don't want them to learn what my data is. So I, the client, I can encrypt my data as shown here. I can send it to the server can compute on it. So it's computing blindfolded. It has no idea, what's inside this box that it's working with, right? It can send me the output of this computation, which I can then decrypt to recover the result. So this magic is something that's afforded by lattices. And then, as I said, we'll move on to topics in quantum cryptography. So this is so far what we've talked about is how to you know, protect against quantum computers when quantum computers go bad, right? But well, if we are in a world with quantum computers, of course we can also use them to do good stuff. So here we'll see how, you know, the unique powers of quantum computation, the no cloning theorem for example, right, allows us to get some really beautiful cryptography that we did not know how to get before, not in the classical regime in particular. So we'll see quantum key exchange, we'll see, you know, quantum encryption, and then we'll see the quantum analog of fully homomorphic encryption that I talked about in the previous slide. Okay, so here our data is again encrypted, and now I'm interested in computing a quantum circuit on this encrypted data. Okay, so this is a snapshot of some of the things that we'll see in this course. I do want to say that you know, it's a bittersweet mix of things. So this course is a little bit like a chart platter. It has a little bit of everything, and I say it's bittersweet because each of these topics, right? So you know, starting with quantum computation, quantum information, this is something you know, really fundamental, very very elegant. You could spend one course, you know, 2 full courses just understanding that. We talked about post-quantum cryptography. So, by the way, before we see post-quantum cryptography, we will also see some pre-quantum cryptography. So, we will talk a little bit about factoring discrete log problems and how to build cryptography from that. So, we will break it before we figure out how to fix it, right? So, you know, this number theoretic cryptography, and then which is broken by quantum, and then the lattice based cryptography that we'll talk about after that, which is currently, so far as we know right now, not broken by quantum. These are very very rich topics in themselves. I mean, I do teach, for example, you know, full courses just on lattice based cryptography or just on number theoretic cryptography. So again, there's some really elegant mathematical structure there, and it's really a fascinating topic to study. And then finally, you know, we'll see quantum cryptography. So, you know, how to leverage the unique powers of quantum computers to actually get things that we did not know how to get before. This is, of course, again a very very rich area of discussion, a very active area of research. All of these are active areas of research, and we'll just get a little taste of that. Okay, so we'll really only get a little bit of taste of all these different wonderful topics, and I regret not being able to go deeper into any one of them. But my hope in offering it in this way is that you know, seeing these things together, I hope will offer a perspective into this subject which perhaps may be missed if we look at any one of them individually. So that is the hope. Let me know via your feedback whether that hope is true or not. And I look forward to you know, teaching this course. I hope that you will enjoy it, and please do let me know if you have any comments or feedback. And I'll conclude by saying that I hope that you know, just as a good appetizer, it whets your appetite for going deeper into any of these topics. Thank you very much.